Hi everyone, thank you for joining in this talk. We are going to be touching upon engineering machine learning system. And the intention for this talk is, or at least for the next 1 hour, is to have a quick dialogue between what are the gaps that we have when we build machine learning systems, and effectively talking about a little bit about machine learning in general, what machine learning is and how we go about, and then focusing quickly on the gaps and stuff that needs to go into building a full-scale system. I'll also have a quick demo where I'll show a containerized app. It's not a great app, it's just a idea of explaining how containers work and the structure around it, which is much more important than the actual app. And yeah, that's the content. And there are a lot of things that this topic covers. This is not a crash course or a course or a workshop. This is just 1 hour probably introduction. So there are a few things which I'm skipping, but I'm trying to stick most to the core. Now let's jump on, right? Let's jump on to the core of this and the machine learning aspect of it. What is that we are trying to do these days, which is very popular trend, right? For the past few years, a lot of trainings, a lot of excitement, a lot of problems, a lot of investments for some of the folks out there in machine learning. And typically these are some. On the left hand side you see one of the most popular examples. You have three different types: unsupervised, supervised, and reinforcement. Maybe something new has come up, I do not know, but these are the three most widely used things. Out of these, supervised learning is the predominant one, kind of regression and classification problems, whether we are doing forecasting, whether we are doing some kind of a prediction, effectively where we know the y variable in the model, right? That's the supervised learning kind of scenario. Classification is more like image classification, text stuff, customer attention, and things like that. So regression classification, need not touch upon it a little bit, a lot. I think that's not the core agenda. Coming back to my slides, the unsupervised learning is where we do clustering, kind of recommender system, customer segmentation, where we do not have a lot of predictions to make. Also, there's lack of, let's say, training data or labeled data. Clustering and PCA dimensionality reductions are very popular, and PCA being a very popular technique, that's one of the things which falls under dimensionality reduction. Now that's RL is as I have understood, it's a penalty and recommendation based system, penalty and loss optimization kind of system. Moving on to the right hand side of the diagram, what we have is typically the most popular library and the cheat sheet for it, where we solve all of these four different problems, which is regression, classification, clustering, and dimensionality reduction, and the way to do it, right? This is very standard. And yes, a lot of feature engineering goes on it. I'm not in any way undermining the role of the effort that goes in here, but that's pretty much what modeling is a lot of about. You understand the problem, you do feature engineering, you solve let's say certain use cases, you come up to a reasonably right forecast accuracy or an accuracy, whatever is the problem domain we are talking. A cheat sheet is not visible. I think this is the cheat sheet I'm referring to, this sklearn diagram. Is my screen visible? Pratik, is it visible to you guys?
Yeah, it is visible.
Yeah, okay.
Maybe you can zoom in a little bit if you have to talk about
Sure.
specifics.
Sure,
Yeah,
sure. I'll probably
yeah,
keep that in mind. All right. So that's the
sure.
cheat sheet. I think if you just search for sklearn cheat sheet, you will find it very straight up on Google. Moving on. Now the goal or the key talk is where we start this, right? And when we develop a machine learning model, and this is just a cartoon. Data scientists, you all are data scientists, right? And what you do is you build a model, right? You'll create a custom designed model. Also, the environment in which you operate is very isolated as far as I have understood and observed the state of things. It's kind of a sandbox where Jupyter Notebooks is the de facto thing, and that's where people work. You'll typically have a notebook, you'll look at the problem, you'll pull a data file, and you'll create a model, right? And a lot of these times people do not even use like Visual Studio codes. Notebook is where most of the cool stuff happens. Now, moving on. This is a little more, let's say, realistic view of things as to what goes on apart from model creation. because you typically have to define a problem. You need to do data ingestion, you need to do data preparation, segmentation, where I think the train test split is something everybody is very familiar with. Then we do model trainings, then there's the candidate model evaluation. And this is kind of a loop, right? You do this iteratively. You take your test data, you train a model, and then you take your validation set, you evaluate the model, and finally on a validation set, you would kind of go for a candidate model evaluation once you have it. Now this kind of is iterative, and steps 1, 2, 3, 6 are kind of something which people mostly understand. To emphasize on something which is the first two, like problem definition and data ingestion, there could be probably a workshop dedicated itself to it, because that's also a disjoint piece apart from modeling, but the focus is more towards the 7 and 8 piece of it. So that's what things realistically happen, right? And we are going to be talking about a little more than that. And this model, this prepare, experiment, and deploy is more closer, or is the closest analogy or a diagram that I can find on internet, or probably even draw myself. Now there's a lot of data preparation which happens. You do all sorts of features engineering, feature scaling, data cleaning up, data imputation, labeling of data, and tons of things happen there, right? Also the where you store the data, how you get the data, all of that falls under the preparatory exercises, right? Under the experiment phase, what we do is we have Jupyter notebooks, and some of the people use Visual Studio Code. This is also becoming very popular now, along with PyCharm, which is also another popular tool. And then you build your model, and you train and test, and you again iterate over it. And then finally you have a candidate model, which is register and manage your model, and then you move on to deploying it. And here is when we can see certain things, keywords start popping up, like web services, monitoring, dependencies, etc. This is not the kind of game which data scientists are used to, right? They are usually worried about the feature sets, pickle files, etc. They are not worried on dependencies, web services, and monitoring, and containers, etc., etc. But this represents a more kind of an end-to-end view of things, and which is where we need to ponder a little bit, and we need to understand what are the things we need to see and address after we do modeling. So after we have modeled a business problem, or after we have let's say created a model, what are the things we are doing, right? We need to understand the integration. How is my system or this model integrated with other system components? How are we doing the data ingestion layer? How are we pulling the data? Multiple technologies, right? They also come into play. My core system could be written in Java or SQL, and then we need to think about how to integrate that. Then comes the deployment, which is, yes, you say as to I am a data scientist, why should I worry about you? The answer, super simple, is a data scientist is probably a person who needs to understand the aspects of other team members. There are other team members, and he needs to be aware of what his or her team does, and they effectively also sometimes need to take an active part in these discussions, right? Because this is not an isolated exercise. You're not doing this in an isolated way. Then we go on to deployment, where we touch upon traditional versus modern approaches, cloud versus on-prem kind of a thing. A lot of you would typically talk to your architects, infra team, but again, something that machine learning systems also need to worry about and cannot escape. Scalability, right? What is that? I mean, as my model, it can always do a model.predict, but can it do model.predict probably for 1,000 users? The pickle file, can it be available in memory all the time? Can it serve concurrent users? Because unless and until a model is used, it's pretty much of not a lot of use, right? It's not a lot of use for people. And then we jump on to the monitoring aspect of it, as to what do we do, what are the things we can do to see the system, and how the systems behave, and assess the modeling, etc., etc. This talk kind of builds upon some concepts, very popular buzzword in the industry, DevOps, wherein we, let's say, the entire life cycle of software development, right? The automation pieces of software development, from coding, planning, monitoring, operating, releasing, building, is kind of an infinite loop. This all kind of happens in a loop, where things are all connected, and they are not sequential. We need to, as we see in these diagrams, things are not sequential. They are kind of very closely connected, and there's a loop that goes on in when we work and talk with these systems. And hence the a more realistic picture, the circular way of seeing things, where you have model training, you deploy it, you scale it along with APIs, you manage it and you connect to it, and then you keep on repeating it. So effectively what we need to have is certain set of practices to shorten the life cycle by probably automation, right? That's the key mantra here. That's the key talk of all of this. And this is when a lot of buzzwords starts popping up, and the most popular right now is machine learning ops, right, which is MLOps, while it's a derivative of machine learning plus probably DevOps, I think, and that's my opinion. There's a very excellent book from which I've taken this diagram. It's called MLOps, Operationalizing Data Science. It's a very short and crisp read, very good in the summary of it. Pretty interesting book if you see. And what we do in MLOps is you typically build, manage, deploy, and integrate. So build, manage, deploy, and integrate, and monitor, and that's the whole life cycle of it, right? In build, what do? We do feature engineering, model building, and testing. In manage, we do auditing, version control, of lot of things, right? We are used to seeing version control for source code, but here we need to worry about model version control for data, for the model files, because effectively there are multiple models that come out and the best one needs to be picked, right? See potential model reuse scenarios. Can the same model be reused in a probably different landscape, or if scenarios are kind of similar in a like-to-like state? Deploy and integrate, model export and deployment, and business app development, where you typically use and start using the model. These are the parts where we start doing more ops than ML pieces of it, right? And then you do in monitor, where you typically measure it across certain matrices, right? These matrices could be anything. They could very easily range from just simple infrastructure monitor, or they could be your model actual versus prediction, right? Because your system is predicting, and let's say it's a defect prediction system, so you're predicting defects and also at the same time you have actual defects, so you could have a performance measure there. And then you have business matrices, which are probably not targeted for this audience. So I'll take a pause here before diving into the, let's say, next segment, and let's do a quick interaction and see are there any questions so far. I've been let's say ranting about for the past 15 minutes, and we have touched upon, slowly moved from machine learning to touch upon DevOps, and also do kind of finally landed on MLOps. Are there any questions? Anybody want to jump in, unmute themselves, or probably use chat? I'll take a pause here. All right, I do not see anything, which is good and bad both. Okay, how is Jaskirat Kaur? She's asking, how is MLOps effective than ML? Pretty good question, right? So ML, machine learning in itself, as we saw initially, machine learning is probably the art and the science of doing data science, of making machine learning models, of solving these problems, right? The ops pieces are where once you have created your model, what do you do with it, which is what the remainder of the talk with it. How do we productionize it? How do we operationalize it? And by operationalization, I simply mean, how do we make sure the model is used by somebody, right? This whole circle where the ML pieces would probably be this part, but then this whole circle needs to still happen, right? Because models themselves are just files, and they are of no use to anyone, because there's a world outside it, right? Apart from being a data scientist, you need to give your model to a consumer. So that's where MLOps comes in. I don't think it's an effective question. Probably yeah, it does certain reach in best practices around how you could do ML also, but it's more like both are required. Sankesh is asking, is it like DevOps? Very much, but probably evolved. There are pieces in DevOps which there are problems that DevOps solves which simply are not present here, and there are problems in MLOps which specifically MLOps address, which DevOps hasn't seen or seen through. But at a very large umbrella, it is like DevOps, that would be true. So the dev part here is replaced by the ML word, which is the modeling, and the other part would be in the operations, which is the rest of the stuff that I've been talking about. Right, I'll move on. Now once we touched and established it, how many mechanisms do we need to know to deploy our code into production? That is the effective question that I ask always, and there could be different teams in your company, probably multiple, more than one, or it could be one if you're in a startup, or could be different demographics. And the second question is, once we have them, let's say once we have defined them, could be multiple, which we'll see in the next few slides, how do we standardize them? And why standardization is important is because if everybody comes up in their own way, imagine you are running a company, and if everybody starts coming up with their own way of building machine learning models and deploying machine learning models, then what will effectively start happening is that there'll be too many technology stack and too many things probably to worry about. The firm might spend a lot of need specialized skill sets, and so the need for standardization is also very important. Right now, if we see this, if we see the last slide, effectively we have lots of it, right? We have tons of different ways of serving model, as the term goes on, right? It's model serving that we talk about. So you have Flask. You could always wrap your model into a Flask API. I'll probably show an example for this and also Dockerize it. You have TensorFlow for Kubernetes, with Kubernetes, sorry, not for, wherein you have TensorFlow deployed on Kubernetes, and one of the very nice ways of doing that is using Kubeflow, which is very popular, which is growing, the popularity of it is growing very rapidly. You have Seldon, which is another framework. You have Microsoft, AWS, Google, all of them have cognitive services of their own, where you can just go and use and follow a SaaS model, and you'll typically be very happy about it. Just get a machine learning model, or you could just probably do something on your own in Python. And this is not an exhaustive list, guys. There's tons more. As we change this, Veka, there's probably SageMaker is already covered. We have Pachyderm, we have something called as Nucleus, which is very popular nowadays. So tons of different model serving frameworks, and I'm just throwing in words here. Now, effectively, to simplify this, what do we do and how do we solve our original question of productionizing a machine learning model? So to simplify, we can either consume a provider API wherein the model is either pre-existing or we have created on our own, kind of auto ML scenario, stuff like that. Or we could build and deploy our application, which consumes a serialized model accessible over an API. And the emphasis is on the serialized model because all the models are saved as a serialized file, which is the pickle file or the feather file or whatever is the file format that you work with, right? These are the things, these are the model files that we typically work upon, right? And now we are going to jump upon one piece of let's say one piece of technology which can help enable let's say the last slide, which can help enable the build and deploy pieces. We'll talk about the serialized part also shortly. Now when we do build once Java, when it, hi, is there a question? Okay, somebody left. All right, so when we have let's say Java folks here, if there are any okay, there's a question. Let me take that because this seems very interesting. What more complexities come into a picture for online learning of model? When model trains continuously in production using real-time data, it receives like. This is a good question, sir. Satyarth, I think I'm gonna come up to these questions very shortly. Yes, you are right. The retraining kind of puts a little dent in the whole schema of things, right? It's very how do I say, not usual way of doing it, because retraining typically involves scenarios where you will need a much larger compute. Also, if you are retraining in real time or almost a near real time scenario, let's say where your model is getting updated every day or something, you need also some sort of a model versioning system. We're going to touch upon some of these briefly and probably lay out the key pointers on the key answers to this. All right, so build once, run anywhere. And why am I talking about this? Because Java once had a notion of let's say write once, run anywhere, and that quickly evaporated, because if you have used a Java application, you know this is not true, because you could probably develop in Windows and it could go haywire on Linux or Mac. Also, it could go haywire on a different machine, or it could go haywire in a production scenario. It's very, very difficult there. Now, but that is a development language. What we are going to talk about is standardizing deployments and doing it through containers. Now, in a traditional scheme of things, and I'm sure all of you have experimented, you could have a Windows laptop here, something like this, which is your infrastructure. Then is your hypervisor, which could be the Windows hypervisor if you're running a Windows, let's say Pro Edition, or it could be WSL2. No, WSL2 does not allow, it allows subsystem, it allows a different layer of virtualization kind of a thing. And then, or a virtual box, very simply, you could think of this blue box as a virtual box. And then you are typically creating virtual machines. And what these virtual machines will have is, let's say the bottom horizontal is Windows, this could be Linux, this could be Ubuntu, sorry, this could be Linux Mint, this could be Ubuntu, this could be Kali. And all three machines would be different. And imagine this further, where your machine had, let's say, 12 GB of RAM, and your core OS is kind of consuming most of it, like let's say 3 GB of it, right? After it, you will have to physically allocate memories into each of them. You do not have a concept of shared. Even if system A and B, VM A and B are not using anything, this application which is running on virtual machine C will be constrained by the memory allocated to it, which means you could have a wastage of infrastructure here. Also, the guest OS kind of eats up some system resources, which is not very good in a let's say production environment. That's where containers come in. That's where containers are outshining these days. And I'm not comparing effectively between a container and a VM. I'm just specifying, because both have dedicated use cases. It's not either or question. It's probably what fits your use case. And in containerization, what happens is you are effectively abstracting your runtime engine, right? You're effectively abstracting your runtime engine. Your applications are packaged in a way that they can benefit from a, let's say, shared memory kind of a practice. So in this environment, in option 2, we have the host operating system, we have Docker, and we have app A. Let's say all of these apps are not consuming in a lot of memory, then app A is kind of free to expand. So Dockers or containers by their nature are more elastic than virtual machines, which is a very key takeaway from this, let's say, talk or the short discussion. Containers are more elastic in the sense of usability of the infrastructure, the CPU and the memory. Also, the amount of time it takes to spin up a container is much faster than a VM. You could typically spend a couple of minutes, or maybe less than a minute, or more than 5 minutes, depending on how bulky your virtual machine is. And that can be done through different mechanisms like ARM templates or things like that. But on containers, they're much faster. They stop pretty fast. So even if they crash, they come up very fast. That's one of the core benefits of it. There's much more, and we'll touch upon some of these, but again, this is not a container specific talk. In a traditional deployment in your machine, what's happening is, and you may be solving this problem like by using a Conda environment or a virtual environment, but imagine if you don't use either, this is what you will end up with. Traditional OS, where on the left hand side you have your machine things, kernel, systemd, Docker, etc., and then you have your whole application stack, Python, Java, Nginx, SQL, ABCD, and then you could have different applications. In this scenario, you cannot run Python application 1 on Python 3 and application 2 on Python 2, simply because you are running a traditional OS and you are not using any kind of wrapping or virtualization. Virtual environments and Conda environments kind of help you achieve it, but you do not really rely on virtual environments and Conda environment in production. That's not the way your servers are structured. That's more of a let's say development kind of a scenario. I'm sorry about that. Sorry about that. So in a container landscape, what happens is you have a machine which is your traditional OS, and again this is a Linux example, but it could be anything. You have a machine where it's containerized, and then your container image typically has everything. It could have, let's say, all the packages it needs, and all of these green boxes are one container images. So each of them are independent and kind of have all the dependencies that they have need to run tagged inside it. If I probably take a more deeper dive, should probably have this before. So the way they are operating, the way containers operate is, imagine, see from the top and then look at the bottom of this stack, right? So you have a base image, which herein is Ubuntu, on top of which everything will run. So you would typically then download Oracle JDK. You would typically download, you will typically then again run that command. So the first run is run the curl command, and the second run is kind of run the tar command. And then you probably again are downloading certain things, and then you're copying it, you're exposing a port, and you're creating an entry point. I'll show this example for a Python application also very shortly in the demo, but this is where containers work. You typically write them top down, where the base image, kind of each of the base is tagged up in this way, and then on the very top you have the, let's say, the read write layer through which you have your entry points exposed and whatnot. So this is how your application would work, right? It will be packaged, and then once you take it onto any machine, it could be any machine, it will just it is just expected to work this way, right? And that's exactly what the workflow also specifies. If you see, what's happening is, this is a host 1, right? This is probably my machine. This could be my machine, right? Host 1, and I created, and then I created a Docker file for it, and I created a container, and then I pushed it to a container registry. What this is going to happen is, this could be my machine learning application with the REST API, Flask API around it, and all the configurations. What will happen is, anybody can pull, probably anybody in the stock can pull that up from their machine and just run it as is. All they need to do is do a pull and do a run command. They do not need to install anything, they do not need to download anything. All they need is Docker, which means that I have successfully packaged my software in a way that it can be distributed without any let's say changes in its properties. There'll be no change of properties required from probably the core code or the core functionality. Yes, we need to still talk about scaling and stuff like that, which we'll touch upon, but that's pretty much it, right? This is the overall workflow. Now moving on, these are some of the simple commands in Docker, right? This is effectively a very simple view of what and how Docker to interact with Docker. You do Docker build, and I'll show you this through an example right now. Is you do a Docker build to build an image. You say Docker images, it will show you all the images. You say run, it will run an image which is an executable container. You say ps, which is similar to the, let's say, Linux px commands. It will show you all running and stopped instances. You do a stop and it will show you, it will just stop it. You do an rm, it will delete it, and which is remove the running instance, not the image of it. Remember, image is like an ISO file, and the instance is the runnable of it. So that's the beauty of it. And then Docker RMI, where you are removing an image. Now let's take a quick demo here. I'll walk through a very short app. The idea is not to kind of overwhelm it, but show it. So this is my app, right? What this is doing is, this has two pieces of technology. There's no while on my machine all of these exist, but I'll show you how it's independent of my machine. So I'm importing OS, I'm importing socket, I'm importing Flask, and I'm importing Redis, which is kind of used to manage a counter here, which for some reason doesn't seem to be working. And all I'm doing is just connecting to Redis. Probably this is where the issue is in my error. But this is a simple app route where on the browser you'll be able to see that hello will be printed, right? And then the counter. This is what is the interesting piece, right? This is where we have the Docker file, which I was specifying that we build from top down. So you say from Python, and what it will do is it will connect to Docker Hub and pull Python. Then you set the working directory and tell Docker, or which is, let's say, the container image, that my working directory is app. And then you copy everything into app. So all my app, my py requirements will be pushed inside it. And then what I need to run is, I'll show you my requirements file. I have just two things, Flask and Redis. But this could be anything. I could install, put anything here, right? The idea is just, I can write 300 different things and all of them will be installed. The important message is they will be installed inside the container. They will be running and installed inside the container. So you typically do a from, set the work directory, copy all your code, and then you do a run pip install where all of your let's say libraries are installed, and then you expose a port, right, outside of which needs to be accessed outside of this container, because the container is in itself and has an operating system. It needs to know what ports will be used. I need to do outside and inside. That's the networking. And then you can have your environment variables set or not set. And then finally you specify run this when the container launches. So you do a cmd and you call python app.py, very similar to what I will do in this, if I were to, let's say, connect to it using a command line, right? So this is my app.py. This is what Docker file is. The Docker file is helping it run it, execute all of the things and install things. The requirement is to manage all my different libraries that I need to install. I'll show you what I did is, just before this I started this and you'll be able to see all of the stuff that happens. So this is where I have built my container. As I showed, it's a pretty simple way. So I told Docker build, and you need to be inside the working directory to be able to run this command, -- tag friendly hello, which is just a name for my container image, and you put a dot. Again, this is very similar to Git, right? You have to put a git add dot, and it will pick all of the things in that folder, right? The first step was from Python, right? What it did is it downloaded the latest image of Python here, right? There's a Python image which has been downloaded to my machine. It changed the working directory, and then there was an intermediate container, it removed it. And this keeps on happening multiple times, the removal of intermediate container, etc, etc. Then the step 3 and 4 were kind of, step 3 was to copy it, and step 4 was to run the pip command. And this is exactly a pip command as you would run on your machine or using a conda environment. So what you have is, you have collected Flask, you have collected Redis, you have collected all the dependencies around it, right? And this could be anything. This could be any application, right? Then you are exposing the image, and then you are removing the interface. You are kind of, let's say, again, removing the intermediate container, and you are exposing the port 80. The environment variable is kind of, I don't think I've used it anywhere, but it's just to show that you can do it. And finally, you will get a successfully tagged message and a warning where, because I'm using a Windows host and the base Python image is using, I believe, Linux, and that's why this error is there. But this hasn't caused me any issues. Now I just did a Docker image ls, where you see that this was created some time back, and it's not really 9 seconds, it's probably 1 hour right now. And then yeah, there are a couple of errors here, and I corrected the port mapping, and you need to specify what port you need to run. So the outside port goes on the right, which is when I specified in my app.py port 80, and the port on which my machine this is running, it's 4001. And as you can see on localhost 4001, I'm just calling this. Now this counter seems to be not working, but this is getting refreshed because this is connected to live server. You see, you're getting a message every time I do this. It's kind of a live. So that's how you typically have a machine learning example. Very similarly, you have a API which is wrapped around it, you package it, and then you kind of deploy it, right? That's effectively the message, and that's pretty much the core idea of this talk, right? Now coming back to Mr. Satyarth's questions, that what more complexities come into picture for online learning of models, right? That's what I want to jump onto now, because that's, and feel free to put up more questions. I'm almost nearing the end of my talk, probably 10 minutes more. Feel free to shoot up your questions or just unmute yourself if you want to jump in. Now we need what containers did is they helped us kind of isolate it, right? If I purely talk from a model learning perspective, then this is a better deck to probably flash. When I need to do my experiment management, I need to take care of model serving, I need to take care of server in let's say integrations, I need to take care of data and model versioning and pipelines and workflow. Also, there are certain things when we go scale, let's say in an e-commerce website, what's happening is data is coming in very fast. So your ingestion layer needs to be capturing that data in some form of probably on an S3 bucket, or whatever is your storage layer, right? And from there we need to pick up the latest files and push it into the retraining scenarios. Also, pushing in the retraining needs to be having a schedule where you could benefit certain things in Kubernetes, something like, let's say, multi-node pool, where you have a node pool which is effectively serving people for APIs and stuff like that, and there's a much larger node pool, let's say a GPU node pool, which is helping you retrain it. So those kind of scenarios also happen. Now some of them are listed here, which is what containers have simply helped us achieve or do is, this is probably running a single instance of it. But what if I need to run multiple instances of it, right? The answer would be run more containers. But how to do that? So Docker, Swarm, and Kubernetes are the and mostly it's Kubernetes, honestly speaking. Docker Swarm is kind of a left away guy most of the times. It's good for proof of concepts and low application needs, but not really a true production system, right? So what we need is a little more than isolation. We need to talk about my scheduling, where my schedules are and where my containers run. What would be the schedule for my API server, because it's going to be live? What would be the schedule for my retraining scenarios, because they need to happen probably every 6 hours or every 3 days or every month, depending on the scheme. So how do we manage the container, let's say, scheduling? That's another challenge. The life cycle and health. Since we are talking real-time systems, no system is going to run happily. There will be failures and there'll be, let's say, downtimes around it. Now, one question would be, how do we respond to those failures? But the primary is, how do we know that a failure is about to happen or a failure has happened? So that's where you have lifecycle and health checks. Kubernetes kind of excels at auto scaling, and those kind of things are also kind of very great at, we'll touch upon that. But on lifecycle and health, Kubernetes gives you a console, very easy console to see and check out things. On Docker Swarm, you have something which is called a Swarm Pit. It's a very intuitive UI which will show all of your nodes, all of your running containers and things like that. So that's some of the technologies you could leverage. Upgrade and rollback, where are your containers now? Let's say you want to push an upgrade, right? You'll typically also have a container registry, because that's where you'll version your code, right? You have versioned your code, you need to version your data, you need to version your model, and very similarly you need to take care of versioning your container, because that container either has the retraining logic or the updated retraining logic or the way model is inferenced, right? You need to think through that. That's your system design, effectively your architecture. Isolation, very important. How do I make sure that my jobs are not interfacing too much and they get the compute that they need? Again, the retraining versus serving kind of comes into picture in this, and the workshop probably that we talked about at the beginning will probably elaborate a little more on that. Scaling, which is again making jobs and clusters bigger or smaller. The retraining scenarios could be something on the lines of, let's say, we need to retrain every 6 hours or probably every 6 months, doesn't matter, and we need a very large cluster, right? We have, let's say, a D tier machine or an A tier machine or a or a micro or mini or a medium machine on AWS, while on training we need a G tier series which has a GPU and needs some NVIDIA proprietary stuff. So all of that cluster management needs to be thought of and designed. Again, very easy to do in Kubernetes. Kubeflow is kind of great at achieving some of the things. We are not touching on Kubeflow today, but we'll certainly do that in the workshop because that's very, very important. Security, continuously scan container images, kind of for security vulnerabilities. An important aspect because VMs are thought to be traditionally much more secure, and in the past few years, or at least last 8 months to 12 months, a lot of things around, let's say, container security has been come out and vulnerability assessments have started to sprout up, right? So that's very, very important to see. Load balancing, again, one of the core things that needs to be taken care when you are running a multi-clustered environment. Provisioning storage, what data to store, what data could be ephemeral, which is what data is transient, what data is persistent storage, and finally logging and monitoring. Log everything that's happening, right? Log your model accuracy, log your data. For example, you have your model suddenly is performing over 95%, and there were spikes of going below to 90 or 85%, right? You would typically want to call out those scenarios very clearly, and if your system does not know what data caused it, what was the anomaly, probably it could be an outlier that flew in the data, and you will not know after that has happened. All you'll have is there was a dip in accuracy, and that could offset your client, right? So logging is also very important. Certain very nice frameworks exist. You could have FluentD, or you could just even rely on Python core logger, which is also very efficient. Also one of the core things which we'll want to talk in the workshop that we have. I'll quickly show the website for Kubeflow. I did not intend it to as a part of my deck, but it kind of warrants itself. Now this is a Google project which kind of builds on top of Kubernetes and is very, very popular nowadays. There are books and courses coming out, and anywhere you're running Kubernetes, you should be able to run Kubeflow. What it does is it helps you manage everything. At least in the machine learning landscape, you have your notebook manager, you have your model training manager, you have serving manager, and it supports multiple different kind of serving frameworks, TensorFlow serving, Seldon serving, etc., etc. You have pipelines where you could just use pipelines where you can schedule and compare runs. You could just do it in a workflow kind of environment and see what its runs are. It's multi-framework. It supports all sorts of libraries and frameworks that exists right now. So very good technology to look at. Coming back to my deck. So that's a little bit about containers, and we need a little more than isolation. And at the end, probably I'll just want to say that this is just the beginning of it. This is probably where we need to think about how do we manage our experiments, because the core world that we want to play in is very, very important. Experiments management, notebooks, where you have, let's say, your Jupyter notebooks, how are you saving it, how is code extracted from it. Model serving, we discussed one approach which is container based. It could be multiple. We could have a batch based serving, we could have a serverless serving, etc. Pipelines and workflows, we have not touched on these, but these are very, very important to touch upon. Serverless integrations, which is data, how do we make sure that our models are only called upon when we need to, right? It could be not a live model that is running all the time. It could be probably once in a while that we need to do. And data and model versioning, very, very important. So these are some of the things which is over and above. So that's what is probably a sneak peek into this. It's not a lot and quite a lot of content.